Hello, this is Mr. Win, and this video is about parametric equations. I'll be going over the examples in the books, just explaining them. So up to this point, we've been graphing single equations involving two variables, x and y, or even r and theta. In this section, we'll study introducing a third variable to represent a curve on a plane. Right, to see the usefulness of this, let's look at this example. Say we throw an object in the air. It's going 48 feet per second at a 45-degree angle. It follows a parabolic or quadratic path because of gravity. So y equals negative x squared over 72 plus x. So we call that the rectangular equation, which we're used to. So here's that picture, part of it, as shown in figure 10.50. Now, this equation does not tell the whole story. All it tells us where the object has been, like its x coordinate and y coordinate. So the x stands for the x distance away from the original spot, and the y is the y distance away. It doesn't tell us when it was at those points. So to determine this time, we introduce a third variable t called a parameter. It's the third variable. It is possible to write both x and y as functions of t to obtain parametric equations. So here they gave us the equation x in terms of t and y in terms of t. Using these two equations, you actually get the x spots and y spots. It's the same graph right here. It's just a different representation that gives us more information. It gives us time now. So it's three variables. So it says when it says equations, you determine that time t equals 0. That just means you plug in 0 for t in this equation and this equation, you'll get 0, 0. If you plug in t equals 3 root 2 over 4 into the top equation, you'll get 36. Into the bottom equation for y, you'll get 18. And when you plug in 3 root 2 over 2 for t in both equations, the x value should turn to 72, the y value will be 0. But now we know where it started, at what time it got to the maximum point, the maximum height of 18, and also at what time it hit the ground. Alright, so this graph has two types of equations that are similar. You can choose the rectangular equation, y equals negative x squared over 72 plus x, or the parametric equation where this introduces t. It gives us the same picture, but with the time parts on it. You do want to find the starting point, and then you want to draw the arrow in what direction you go, and I'll show you that in the next example. By the way, that is called a plane curve. So basically, if you introduce a third variable t, a parameter, on some interval, when you get all those points by doing x of t and y of t, and plot them, that is called a parametric equation, or plane curve. Alright, so sketching. When sketching a curve, you still plot points in the xy plane. Each coordinate xy is determined from a value chosen for the parameter t. Plotting the resulting points in the order of increasing values traces the curve to a specific direction. That's called the orientation. That's where we have to draw arrows. So in this example, it says sketch this parametric equation. X equals t squared minus 4 and y equals t over 2. In the interval negative 2 is less than or equal to t, less than or equal to 3. So first, we're going to plug those in. So we're going to plug in negative 2 for t. Well, negative 2 squared is 4, minus 4 is 0. So x is 0 when t is negative 2. Plugging right here, y equals negative 2 over 2. That reduces to negative 1. Alright, then I'll try another one, negative 1. So negative 1 squared is 1. 1 minus 4 is negative 3. Then here, that's negative 1 over 2. That doesn't reduce. You can do it for all the points in order. Then you graph them. Notice the t part is on the graph, those dots, but t isn't x-axis or y-axis. That's the normal x, y we've been using. So 0, negative 1 is starting point. So right here is at 0 for x, negative 1 for y. That's when t was negative 2. Then when t was negative 1, it was x was negative 3. That goes left 3. Then up 1/2. This is going by 2, so here's left 3, down 1. Then at 0, you had negative 4 for x, 0 for y. So negative 4 for x, 0 for y, that's when t is 0. And then here's where t is 1, t is 2, t is 3. Alright, so plotting it, we obtain the curve C in this picture. The arrows indicate the orientation as t increases from negative 2 to 3. So if a particle were moving on this curve, it would start at 0, negative 1 and move along this curve all the way to 5, 3 over 2. Alright, now note, the picture does not define a function. This fails the vertical line test. But that's actually a good thing because parametric equations can graph more than just functions. It's more universal. Now, interesting thing is, there's more than one way to write this equation. Often there's multiple parametric equations that have the same graph. For example, this other equation, x equals 4t squared minus 4, and y equals t, for this interval gives the same exact picture. But if you compare the values of t, notice this one's faster. This one goes from -1 to 3 over 2, while this one goes from -2 to +3. So 5 points here, while this is less, or a range of 5, I should say, and range here is 2.5. Right, so since more rapidly because t is time, there's applications where parametric representation can be used to represent various speeds at which objects travel along the path. This one's going faster because there's less time to do the whole thing. All right, another type is eliminating the parameter. Example 1 uses simple point plotting, but that can take a while. So we can actually kind of change or convert the parametric equation into a rectangular equation by eliminating the parameter, getting rid of the extra variable. It's actually very simple. You just solve one of the original equations for t. So they did the bottom one. They multiply by 2. You get t equals 2y. Once you have t for one of them, you just plug into the other equation. So now your next equation just has x and y, and just simplify it. So when you go back to a single equation of 2 variables, that's rectangular. All you do, again, solve for t, plug it in. So really, these two equations, the parametric equation is actually x equals 4y squared minus 4. That is a sideways parabola with this vertex. And it does say when converting equation parametric rectangular, you may need to alter the domain of the rectangle so that its graph matches the graph the parametric. This means there are domain restrictions, so we'll see that in the next example. So here's one. Sketch this curve represented by the equations. Here's x equals this equation with t, y equals this equation t. So we're going to solve for t in one of the equations. They chose to solve the first equation. So first they squared both sides to get x squared equals this. Then they multiplied by the denominator. Then they could distribute and then solve for t by moving things over and dividing. But you'll eventually end with this. Once you know what t equals, you just plug into other equations. So they went to equation y and plugged in this big fraction for t for the top and for the bottom. That's where they got these. Then you simplified it, and they got 1 minus x squared. Well, that's a parabola upside down with that's negative x squared plus 1. Alright, so from this rectangular equation, you recognize the curve of the parabola opens down, vertex 0, 1. This rectangular equation is from all axes. Parabola has the domain of all real numbers. But if you go to the parametric equation, you see the square root here. You cannot square a negative number. It's imaginary. So t cannot be smaller than -1. You could square root 0, but not -1. So it says it's defined only when t... Oh, and then also it can't be -1 here, because -1 plus 1 is 0, can't divide by 0. So it has to be bigger than -1. Alright, so here's the picture. So it's half of a parabola, and they plugged in a -0.75 over t, got this first point, and they plugged in t is 0, got the second next point, plugged in t equals 3, got this third point, but they're going upwards. Alright, by the way, it's not necessary for the parameter to be t. It does not have to be time. It could be an angle. So notice there's two equations, x and theta, y and theta. So angles, trigonometry. We got to eliminate the parameter, the angle theta. We could graph this by plugging in instead of t's, plugging theta, like you can do 0, pi over 4, pi over 2, pi, and stuff. But we can solve for cosine theta. So just divide by 3 both sides. Solve for sine theta, divide by 4. Then use the Pythagorean identities. So cosine squared plus sine squared equals 1. Then you substitute, and then you simplify, and notice you get an equation of an ellipse. If you don't recognize the ellipse yet, don't worry, we will be doing conics soon. But it's a rectangular equation, ellipse, center 0, 0, has these vertices with a minor axis there, length, that. And this is going counterclockwise. So for example, I plug in 0 for theta. Cosine 0 is 1. 1 times 3 is 3. So x is 3. And then I plug in 0 for theta here. Sine of 0, 0 times 4 is 0. So we know it starts at 3, 0. X is 3, y is 0. And then it goes upwards. Alright, examples 2 and 3, it's important to realize that we eliminated the parameter to help us sketch the graph. But that just shows us the picture. We usually need the time. So if the graph is usually not enough, you just draw the parabola, you don't know what's happening in the middle. So you need the parametric equations to tell you position, direction, and speed. So rectangular equations can only give you the picture without telling you the exact times things are happening. Parametric equations have that third variable, time, where they can actually be more specific, where they give you t equals this, here's that point, t equals this, here's that point, t equals this, where's that point. All right, now we have to do the reverse. Instead of going from parametric to rectangular, given two equations, get one equation, can we do the reverse? And the answer is yes. It's not that hard. But remember, there's more than one way, one equation. So we went back to this picture. Notice there's two of these have the same picture, even though they had the same original equation, wherever it was. This thing, negative x squared over some t plus x. So let me explain how to do it. So it says find the set parametric equations to represent the graph of y equals 1 minus x squared using following parameters, t equals x for the first part and t equals 1 minus x for the second part. Well, notice we have one equation here, rectangular form. If you want parametric, just introduce a new variable t, and you just set x equal to t. So that's what they said right here. So they already gave us the first equation. Just plug into the original equation. So y equals 1 minus x squared. Well, x squared turns to t squared. So we're done there. But you can do anything you want. So you can say x equals t, you can say x equals t plus 1, you can say x equals t squared plus 50t. It gets more complicated, but if they let t equals 1 minus x, well, we already have the first equation. X is this equation in terms of t. Then you go to plug this x into the original equation. So y equals 1 minus x squared turns to 1 minus t squared. You FOIL that combining terms, you get 2t minus t squared. So this picture is that graph. It's a parabola. Notice we start here, and then we're going this way. All right, last slide. If given, so the summary slide. If you're given an equation in parametric form, meaning you have two equations, you need to be able to graph it by plugging the t values. If they give you an interval, use those numbers. Use the leftmost number, the smallest, then go to the highest and find numbers in the middle. But if they don't give you an interval, you can make up your own. That's fine. And then also be able to convert to rectangular form by solving one of the parametric equations for t and then plugging that t into the other equation. Alright, and then if you're given an equation in rectangular form, meaning one equation with x and y, be able to change it to parametric by setting the x to whatever you want and plugging to the original. The easiest option, like earlier, is x equals t, but if you want to, you can make it complicated, x equals 5t squared minus 2t. But you introduce the third variable. One last thing is this. It is possible to use a graphing calculator to graph in parametric. Here are the steps. In the calculator, you're going to go to mode. So we've already talked about polar. We're now in parametric. Once you're in parametric, you can go to y equals. It now has x1 in turn t and y, the quantization in turn t. So that's what this t comes from. So we're going to type both equations. I'm going to use the same picture right here. So x equals t squared minus 4. And then y equals the fraction t over 2. Alright, last you press window right here. And you must, this is required, set the minimum max values of t because that's the parameter we're introducing. We have to know what we're going to plug in. Otherwise, we'll plug in every possible value of t. So t min, this one says negative 2. T max says 3. And the step, you can do whatever you want. I'll just do 1 because that's what it's doing. It goes from negative 2, negative 1, 0. You can change x min, x max. You don't have to, but it'll make the graph better. So I don't need to go x to negative 10. Let's just go to negative 6. To positive 6 for x, and for y, it looks like I went from negative 6 to positive 6. So I'll do that as well. Negative 6, positive 6. Once I graph this, notice there's the picture. Alright, remember, you must set the min-max values for t. That is required. Alright, that's it for the video. Make sure you ask any questions. Make sure you join the live sessions. There are no questions about this on Get Math, so we will be doing a bunch during the live sessions. Alright, thanks for watching. See you soon. Bye.